Dear students, I am Vandana. Last class we discussed problems of sandwich theorem. In this class I want to explain about monotone convergent theorem. Before going to explain that, I want to explain about monotone sequence definition. See here, what is the definition of monotone sequence? Any sequence is said to be monotone sequence if it is either increasing or decreasing sequence. If our sequence is increasing sequence, then we can say that that sequence is monotone sequence. Similarly, if our sequence is decreasing sequence, then we can say that that sequence is monotone sequence. Now the question is, what is increasing sequence? What is decreasing sequence? Increasing sequence in the form of S1 less than or equals to S2 less than or equals to S3 less than or equals to and so on. The terms of the sequence in the form of S1 less than or equals to S2 less than or equals to and so on. This is the form of ascending order. If our terms in the form of ascending order, then we can say that that sequence is increasing sequence. This we can write Sn less than or equals to Sn for n less than m. This is a condition for increasing sequence. When we say that this is decreasing sequence, if the terms of the sequence in the form of S1 greater than or equals to S2 greater than or equals to S3 greater than or equals to and so on, then we can say that that sequence is decreasing sequence. This is also we can write Sn greater than or equals to Sn for n less than m. Okay, this is the increasing sequence. This is the decreasing sequence definition. Also we have strictly increasing sequence definition, strictly decreasing sequence. Strictly increasing sequence. This is nothing but if the terms of the sequence in the form of S1 less than, S2 less than, S3 less than and so on. If the terms of the sequence in the form of S1 strictly less than S2, S2 less than S3, then we can say that that sequence is strictly increasing. Or else, if the terms of the sequence in the form of S1 less than or equals to S2 less than or equals, then we can say that that sequence is increasing. Similarly, strictly decreasing sequence is nothing but S1 greater than, S2 greater than, S3 greater than and so on. If the terms of the sequence in the form of S1 greater than, S2 greater than, S3 and so on, then we can say that that sequence is strictly decreasing. Or else we can write S1 greater than or equals to, S2 greater than or equals to, then we can say that that sequence is decreasing sequence. These are the definitions for monotone sequence. So these are the definitions for monotone sequence. See here, a sequence is said to be increasing sequence. When we say that increasing sequence, if S1 less than or equals to, S2 less than or equals to and so on, Sn less than or equals to Sn plus 1. This also we can write Sn is increasing sequence if and only if this is nothing but Sn less than or equals to Sn for n less than m. Similarly, strictly increasing is nothing but if the terms in the form of S1 less than, S2 less than, S3 and so on, Sn less than, Sn plus 1 and so on, then we can say that sequence Sn is strictly increasing if the terms of this sequence in the form of Sn less than Sn for n less than m. Similarly for decreasing sequence, here we have the terms in the form of ascending order. See here, the terms in the form of descending order. Same. Strictly increasing is nothing but strictly less than. Strictly decreasing is nothing but strictly greater than. What about monotone sequence? Monotone sequence is a sequence if it is either increasing or decreasing sequence. Then we can say that that sequence is monotone sequence. Next, monotone convergent theorem. This is very important essay for your semester exams. Don't miss to watch this video. Okay, see here, monotone convergent theorem. Sometimes they may ask state and prove monotone convergent theorem. At that time you need to write statement also, or else they may ask like this also. A monotone sequence is convergent if and only if it is bounded. Or else another statement for this question is sequence Sn is bounded increasing sequence if and only if limit Sn is equals to supremum of sequence Sn such that n belongs to capital N. Second bit, sequence Sn is bounded decreasing sequence if and only if limit Sn is equals to infimum of Sn such that n belongs to capital N. Questions are different but the answer is same. See here, monotone sequence. What we have here? Increasing sequence, decreasing sequence is nothing but monotone sequence. What we have here? Boundedness, convergent. Limit value is equals to, if limit Sn is equals to L, then we can say that Sn converges to L. Similarly, limit Sn is equals to some value. What is our value here? Supremum of Sn. So, we need to prove that Sn is convergent. Here also Sn is convergent. What we have here? Monotone sequence is convergent. Statements are same. Okay? So, you need to write the proof. You need to write the same proof for these questions. Okay? See here, what is our statement? A monotone sequence is convergent if and only if it is bounded. So, first we need to consider a monotone sequence. So, let sequence Sn be a monotone sequence. Next, we need to prove this sequence is convergent if and only if it is bounded. If and only if condition is nothing but, first we need to suppose first condition, then we can prove that second condition. Similarly, converse part. Suppose the second condition, we need to prove first condition. Okay? What is our first condition here? Convergent. So, we need to suppose our sequence is convergent sequence. So, suppose sequence Sn is a convergent sequence. So, it converges to some point. Convergent to some point, some limit L, where L is any real number. So, by the definition of convergent, we can write for any epsilon greater than 0, there exists n belongs to z plus such that mod Sn minus L less than epsilon for n greater than or equals to m. This is the definition for convergent, right? From the definition of convergent, we can write any epsilon greater than 0, there exists a positive integer m belongs to z plus such that mod Sn minus L less than epsilon for n greater than or equals to m. This is a condition from the definition of convergent sequence. Next, by using this condition, we need to prove sequence Sn is bounded. So, what is our claim here? Sequence Sn is bounded. So, to prove boundedness, it is enough to prove our sequence is bounded above as well as bounded below. So, that is our sequence is bounded above and bounded below. If we prove these two conditions, then we can say that directly our sequence is bounded sequence. By using which condition we need to prove that condition? Convergent sequence. So, by using this condition, we need to prove our sequence is bounded sequence. Since mod Sn minus L less than epsilon for n greater than or equals to m. This is our condition. By the definition of modularity, we can write minus epsilon less than Sn minus L less than plus epsilon. Add L throughout the inequality. L minus epsilon Sn minus L plus L will get cancelled. L plus epsilon. L minus epsilon less than Sn less than L plus epsilon. Now we have Sn has least element, least elements, Sn has greatest element. What is the definition of bounded above and bounded below? If it has upper bound, then we can say that that sequence is bounded above sequence. If it has a lower bound, then we say that that sequence is bounded below sequence. So I am considering here, let K1 is equals to minimum of, what are the terms of the sequence? S1, S2 and so on up to Sm minus 1. Why? Because we considered here n greater than or equals to m. So we need to consider elements of S1, S2 and so on up to Sm minus 1 with including L minus epsilon. This is a minimum of all terms of the sequence. I am considering that is equals to K1. Next, K2 is nothing but maximum of S1, S2 and so on up to Sm minus 1 including L plus epsilon. So this is the least element, this is the greatest element. So least element of the sequence is nothing but lower bound of that sequence. Greatest element of that sequence is nothing but upper bound of the sequence. So from this we can write, substitute here, K1 is the minimum of all terms of this sequence including L minus epsilon. So in place of this we can write K1 less than, next K2 is the maximum of all terms of the sequence including L plus epsilon. So here we can write Sn less than K2. From this we can write K1 less than Sn and Sn less than K2. So from this we can write K1 is a lower bound. So that is nothing but sequence Sn is bounded below. Next K2 is the upper bound. So our sequence Sn is bounded above sequence. If our sequence Sn is bounded below and bounded above, then we can see that our sequence is bounded sequence. See here. So our sequence is bounded above and bounded below. So our sequence Sn is bounded sequence. In first part we need to prove this condition only, right? This is what we need to prove. Sequence Sn is bounded sequence. First we supposed our sequence is convergent sequence. Finally we need to prove our sequence is bounded sequence. We used the definition of convergent sequence definition. So by the definition we considered mod Sn minus L less than epsilon. From this we can write minus epsilon less than Sn minus L less than plus epsilon. Throughout the inequality add L. L will get cancelled. We remain with L minus epsilon less than Sn less than L plus epsilon. By using this condition we proved finally sequence Sn is bounded sequence. To prove sequence Sn is bounded, it is enough to prove our sequence is bounded above and bounded below sequence. So by the definition of bounded above and bounded below sequence, we need to find a least element, right? For bounded below sequence we need to find a least element. So I am considering K1 is a minimum of all the terms of the sequence L minus epsilon. I am considering here up to Sm minus 1. Why? Because our condition here n greater than or equals to m. So I am considering up to Sm minus 1 only. See here. Next, maximum of S1, S2 and so on Sm minus 1 including L plus epsilon. So minimum of all the terms of the sequence is K1. See here, for example, minimum of 1, 2, 3, 4. From this we can write 1. But we don't know, right, terms of the sequence S1, S2, Sm minus 1. So I am considering minimum of these terms is K1. Similarly, maximum of these terms is K2. So I just substituted K1 less than Sn less than K2. From this we can write K1 less than Sn, Sn less than K2. This is nothing but sequence Sn is bounded below. From this we can write our sequence Sn is bounded below. From this we can say that our sequence is bounded above. Here K1 is a lower bound, so we can write our sequence is bounded below. Here K2 is upper bound, so our sequence is bounded above. If our sequence is bounded below and bounded above, then we can write our sequence Sn is bounded sequence. Okay, first part completed. We supposed our sequence is convergent. We proved our sequence Sn is bounded sequence. Now converse part. See here, converse part. Conversely, we need to suppose second condition. Then we need to prove first condition. What is our second condition here? Sequence is bounded. So I am supposing sequence Sn is bounded sequence. Now we need to prove that our sequence Sn is convergent by using bounded sequence definition. What is the definition of a bounded sequence? If our sequence is bounded above and bounded below, then we can write our sequence Sn is bounded sequence. So suppose that sequence Sn is bounded sequence. By the definition we can write sequence Sn is bounded above and bounded below. Next, now we need to prove our sequence Sn is convergent. Now we need to prove our sequence is convergent in two cases. In case 1, we need to consider first our sequence is bounded above. Next, in second case, we need to consider our sequence is bounded below. If it is bounded above sequence, then we can prove that finally our sequence is convergent. Similarly, for bounded below sequence, we need to prove our sequence is convergent. So case 1, if sequence Sn is bounded above sequence. Yes, right? So I am considering here, suppose sequence Sn has supremum, say K. Why I am considering this condition? Why? Because our sequence Sn is bounded above sequence. Bounded above is nothing but it should have upper bound. If it have upper bound, then also exits least upper bound. Then that sequence also exits least upper bound. Suppose my sequence is 1, 2, 3, 4, 5. 5 is the upper bound. So we can write 4 is the least upper bound of the sequence. If the sequence have upper bound, then there exits definitely least upper bound. So my sequence is bounded above sequence. So there exits upper bound. From that we can write there is also a least upper bound. Least upper bound is nothing but supremum. So I am considering sequence Sn has supremum, that is K. So supremum Sn is equals to K. From this we can write supremum Sn is equals to K. Supremum Sn is equals to K. So K is the least upper bound. Least upper bound is nothing but it should be the upper bound of the sequence. So Sn less than or equals to k for all n. Okay. Next, since our sequence Sn is monotone sequence, first we consider our sequence Sn is monotone sequence. Monotone sequence is nothing but, by the definition, that is increasing sequence, next decreasing sequence. So our sequence Sn is, since our sequence Sn is, I am considering here our sequence Sn is increasing sequence. Okay. Now I am considering our sequence Sn is increasing sequence. By the definition of increasing sequence, Sn less than or equals to Sn for m less than n. By the definition we can write this condition, right? This is also we can write Sn greater than or equals to Sm for m less than n. Keep it one side. Since k is a upper bound, right? Since k is the upper bound, k is the upper bound of sequence Sn. For epsilon greater than 0, k minus epsilon is not a upper bound of the sequence. S, right? If k is a upper bound, if we subtract something from k, that should not be the upper bound of the sequence, right? So k minus epsilon is not a upper bound of the sequence. Epsilon is not a upper bound of the sequence Sn. If it is not upper bound of the sequence Sn, there exists an upper bound which is greater than k minus epsilon, right? So there exists a m belongs to z plus such that Sm greater than k minus epsilon. Now our upper bound is Sm greater than k minus epsilon. So k minus epsilon is the least one, Sm is the greatest one. So from this we can write Sm is the upper bound of k minus epsilon. Since Sn greater than or equals to Sm, since Sn greater than or equals to Sm, now we have Sm and Sm greater than k minus epsilon. From these two conditions we can write Sn greater than or equals to Sm, which is greater than k minus epsilon. So this is nothing but Sn greater than k minus epsilon. If we have greater than or equals to greater than inequality, then we must and should write greater than symbol only. So Sn greater than k minus epsilon. So from this we can write k minus epsilon less than Sn. Keep it one side. Consider this as equation 1. Next, since Sn less than or equals to k, since Sn less than or equals to k, Sn less than or equals to k, and k always less than k plus epsilon. 1 always less than 2. Next, 2 always less than 3. 1 always less than 2. 2 always less than 3. Like that, k always less than k plus something. So I am considering here k less than k plus epsilon. So from this we can write Sn less than k plus epsilon. Consider this as equation 2. Next, from equation 1 and 2 we can write from equation 1 and 2 we have k minus epsilon less than Sn, which is less than k plus epsilon. See here, for epsilon greater than 0, we have k minus epsilon less than Sn less than k plus epsilon. This is we can write, subtract k throughout the inequality. K will get cancelled. We remain with minus epsilon less than Sn minus k less than epsilon. From this we can write mod Sn minus k less than epsilon. So therefore, mod Sn minus k less than epsilon for n greater than m. First we considered, so for epsilon, therefore for epsilon greater than 0, there exists a m belongs to z plus such that mod Sn minus k less than epsilon for n greater than m. This is the definition for convergent. So from this we can write our sequence Sn is convergent to k. We can also write like this, right? Limit Sn is equals to k. Since k is supremum, so supremum of Sn such that n belongs to capital N. This is what we need to prove, right? Our sequence is convergent. Limit Sn is equals to some value, that is supremum of Sn such that n belongs to capital N. In case 1 we considered our sequence is increasing sequence. Next finally we proved our sequence is convergent to k. In last case we consider sequence Sn is bounded above. Next we need to prove our sequence is convergent if it is bounded below also. So I am considering first our sequence Sn is bounded below. Sn has infimum say L. Last case we have bounded above case. So there exists supremum. Now we have bounded below, lower bounds. So here we supposed our sequence Sn has infimum. From this we can write supremum of Sn is equals to, infimum of Sn is equals to L. So L is the least one, greatest to lower bound. Infimum is nothing but greatest to lower bound. So greatest lower bound is L. So L is also the lower bound of the sequence. From this we can write L less than or equals to Sn for all n. Next, since sequence Sn is decreasing sequence, since our sequence is monotone sequence, so it is either increasing or decreasing sequence. Now I am considering sequence Sn is decreasing sequence. So from this we can write by the definition Sm greater than or equals to Sn for m less than n. Okay, keep it one side. Next, since L less than or equals to Sn, so L is the lower bound. For any epsilon greater than 0, L plus epsilon is not a lower bound of the sequence. Lower bound of the sequence Sn. If it is not a lower bound of the sequence, there exists another lower bound, right? So there exists m belongs to z plus such that Sm less than or equals to L plus epsilon. So Sm is the least one. So Sm less than L plus epsilon. So here Sm is a lower bound. L plus epsilon is not a lower bound. So there must and should exist another lower bound of L plus epsilon. So Sm less than L plus epsilon. Since we have Sm greater than or equals to Sn for m less than n. This we can write Sn less than or equals to Sm for n greater than m. From these two conditions we can write also Sn less than or equals to Sm and Sm less than L plus epsilon. From these two conditions we can write Sn less than or equals to Sm, which is less than L plus epsilon. That implies Sn less than, strictly less than L plus epsilon. Keep it one side. Consider it as equation 1. Next, see here, since L less than or equals to Sn. Since L less than or equals to Sn. Clearly we can write L minus epsilon less than Sn, which is less than or equals to Sn. S, right? Clearly L minus something is less than L. 1 is always less than 2. Like that only, if we subtract something from L, that should be the least one, right? So L minus epsilon less than L, which is less than or equals to Sn. So L minus epsilon less than Sn. Consider it as equation 2. From 1 and 2, L minus epsilon less than Sn less than L plus epsilon. Now we get L minus epsilon less than Sn less than L plus. Now we have L minus epsilon less than Sn less than L plus epsilon for n greater than m. Subtract L throughout the inequality. Sn minus L, L plus epsilon minus L for n greater than m. L will get cancelled. So we remain with minus epsilon less than Sn minus L less than plus epsilon for n greater than m. From this we can write, starting we took epsilon greater than 0. There exists m belongs to z plus such that from this we can write mod Sn minus L less than epsilon for n greater than m, right? So finally we get mod Sn minus L less than epsilon for n greater than m. This is the condition for convergent. So therefore sequence Sn is convergent. Convergent to L, right? Sequence Sn is convergent to L. From this we can write limit Sn is equals to L. L is nothing but infimum of sequence Sn. So from this we can write infimum of Sn such that n belongs to capital N. This is what we need to prove, right? We proved our sequence Sn is convergent in both the cases. In bounded below case also our sequence is convergent. In bounded above case also our sequence Sn is convergent. So therefore sequence Sn is convergent. Okay. So from this we can write a monotone sequence is convergent if and only if it is bounded. This is a proof of monotone convergent theorem. So if you have any doubts regarding this, you can ask me. Okay, watch this. Don't miss to watch this video. Watch this video 2 or 3 times. Then you get more idea about this. Do like, share and subscribe my channel. Thank you.